Hi everyone, I'm Elena. I'm a data engineer here at Gousto, and today Dan and I are going to share with you our secret recipe for building robust and scalable data pipelines with ΑLaSpark. In today's session, I'm going to firstly introduce you to what we do at Gousto and the data lake architecture we built in the past year and a half to give you some context of our scale and complexity. I'm then going to walk you through some of the difficulties of building data pipelines at scale and explain what ΑLaSpark is and what problems it solves. To show you how simple it is to get started with ＡLaSpark, Dan is going to give you a quick live demo of implementing a new Spark pipeline from scratch, to then go into details on the specific ＡLaSpark components and design patterns. We'll have some time at the end to talk about what's next and for any questions you might have. So, a bit about Gousto. We're one of the UK's top recipe box companies and the leader in choice. Our customers have more than 75 recipes a week to choose from. You select your favorite recipes and we deliver the precise ingredients and quantity to your door, so you can cook delicious meals with none of the hassle. But mostly, we're a data company that loves food. We have a big focus on data-driven capabilities, such as accurate recipe recommendations, optimized weekly selection of recipes, efficient order allocation across a multi-factory network, and highly optimized factory layout. All of this is driven by the data that we deliver in data engineering. We currently have a wide variety of sources from which we ingest data. These include things like multiple factories emitting events, various database systems behind factories or our e-commerce platform, and multiple third-party APIs. We primarily use AWS services to ingest data into the first stage of our lake, including DMS, Lambdas, Kinesis Firehose. We then store our data in a variety of raw formats, which is ingested to our cooked layer as Delta, which is the single source of truth for the business. From here, we model data using dbt on Spark to populate our most curated served layer. Our data is then used directly from our lake for a variety of use cases, such as BI analytics, factory and supply chain operational reporting, machine learning and AI, and marketing. During the past year and a half, we've faced many data engineering challenges at Gousto. This was because of the wide variety and quantity of data that our systems generate and process, and the low latency requirements for this data to be available for analysis. Our main goal was to ingest everything from our raw layer into one single target, our cooked Delta Lake. Our first major requirement was the data from Factory 1. On one side, we have the pickline data. These are all the events related to the life cycle of a Gousto box inside a factory. They are sent in CSV files that need to be ingested in a batch job and written to Delta in a PEP mode. On the other side, there's the inventory and stock factory data stored in a database on which we want to perform change data capture and have data available in near real time. Now, these two on their own should be a pretty trivial use case for building an ad hoc pipeline. However, what happens when Factory 2 comes along? Factory 2 pickline data is indeed completely different from Factory 1's. Arriving in small JSON files through a message bus, it features 60+ different messages that need to be processed in a streaming fashion. And here's where the complexity starts to increase. As you can imagine, the pickline system events are physical events generated from a third-party system running in the factory that we have no control over, and that is specific to that single factory. We have 4 factories in the UK so far and more to come very soon. Whatever we build to ingest this data has to be flexible, able to scale and adapt to the changes that will be required to handle N+ factories. Along with the factories, there's also the data coming from the e-commerce website database that deals with customer orders and subscriptions, which contains more than 300 tables, and we were expected to deliver with change data capture and almost in real time. Now, add several third-party APIs and other internal systems on top of all of this, and it's pretty obvious that solving this case by case is not going to scale, and it's going to be unmanageable in the long term. The resulting data platform will probably feature numerous data pipelines with bespoke Spark code, which will often remain untested. there will be a lack of coherence among the different ingestion processes. Enforcing naming conventions and standardized logging, monitoring, alerting will be almost impossible. But mostly building new data pipelines from scratch and productionizing them will probably take weeks to months. So how can we do better? This is where ΑLaSpark comes in the picture. ＡLaSpark is a wrapper around Spark that provides pipeline functionalities to quickly build data pipelines at scale. It offers specific, reusable, documented, and unit-tested components that can be mixed and matched together depending on your use case and requirements. Think of it as pre-measured, pre-packaged, ready-to-use ingredients for your new recipe. All of these components provide standardized logging, enforce naming conventions, and automatically handle metastore interactions where needed. They're also relatively easy to use. Whatever your background, this will simplify the process of getting the data where you need it. ΑLaSpark has allowed Gousto's engineers to focus their efforts on building robust pipelines rather than rewriting unmanageable code. But let's start by taking a look at what these ΑLaSpark components are. All the data ingestion processes, in one order or the other, take care of three main operations: extracting the data from a given source, transforming this data according to specific requirements, and loading it into a target, or ETL, as we know it. This is why we've divided ΑLaSpark components into three main categories: readers, processors, and writers. The function of these components is pretty straightforward. Readers are for extracting data from a source and handling metastore interactions, and they would differ based on the source, the file format that we're ingesting, or if we want to create a batch or stream job. Processors allow you to do small, specific transformations to the data, whether it's at table level, column level, or row level, like adding or dropping partitions, columns, removing duplicates. Writers behave very similarly to readers, as they're also divided based on the target, the file format that we're writing, or if we want to create a batch or stream job, and automatically handle the interactions with the metastore. Writer can be used multiple times across one pipeline. All of these components can be concatenated together as needed, starting with a reader, followed by multiple processors and writers, one after the other. Let's take a look at how this can be done. Here's an example of a streaming pipeline in ΑLaSpark, in which we are ingesting Parquet files, making some transformations, and then writing it to Delta using the append mode. In this case, we're looping through all the tables contained in a given source database in a metastore. At the beginning of the job, we set a pipeline name. This helps group different pipelines in different stages for things such as bed records and checkpoints. For example, all of our brought-to-cooked pipelines will have checkpoints in the same location. Then we apply a reader to the table using the function .read, and we tell it to use Parquet stream reader as our source data is stored in Parquet files. We can now start concatenating all the processors and writers we need for this pipeline. In this case, we're using two processors, some processor and some other processor, to apply some transformations to the underlying data frame, and one writer at the end. The streaming writer will write to the target database in format Delta, and with the streaming output mode set to append every 5 minutes. Going back to the data engineering challenges we talked about at the beginning, building all of those pipelines is now as easy as cooking a Gousto recipe. As we build pipelines for different sources, we make sure that all the functionalities we build for one pipeline has a small, specific function and is reusable in the future. So once we create the factory one pickline data pipeline, we have a CSV reader, some processors with common transformations, and an append writer. So when factory 2 pickline comes along, all we need to do for now is only building the JSON specific reader and some utils. Everything else has already been written, tested, and implemented. Same for the inventory and stock database. Once we build the main components with ΑLaSpark, we can then reuse them for all the factories we expect in the future, so that ingesting data from new factory requires simply some configuration changes. These ready-made components can be now reused and concatenated as we please. as in the example for ingesting the e-commerce website, where we can concatenate writers and processors to write to a different location, for example, the PII data, before masking it and writing it to the usual target. This is the strategy we followed at Gousto, and it's what been enriching ΑLaSpark of useful and diverse functionalities. Thanks to this, we built our entire data lake from scratch within less than 2 years, which now ingests more than 500 gigabytes of diverse data each day in near real time. Over to Dan now to show you how to use ΑLaSpark.
Hi, I'm Dan, and I'm also a data engineer here at Gousto. And today I'm going to be giving you a demo of ΑLaSpark, as well as going into a deep dive on how ΑLaSpark works. We're going to use ΑLaSpark to build a pipeline to process some raw CSV data into a process bucket for downstream users to query. At Gousto, this would usually mean leveraging the streaming capability of ＡLaSpark with Databricks Autoloader. However, for the purpose of this demo, we're going to be operating in batch mode. This is just so that we can more easily access the underlying data frame to show you what's going on under the hood. We've already set up a raw metastore and added a schema to the table. This will be used as the source of the pipeline. And lastly, there's an expectation that this data will be used frequently by downstream users who don't want to wait forever for their queries to run. For this reason, we're going to pick a sensible file format and partitioning scheme to their benefit.
We have created a metastore database and a table which will allow us to read the data that is currently residing on AWS S3. The database is named Glue Raw Databricks Summit, and the table created inside it is named Fake Web Events CSV. They have been created like so, with the following SQL executed in this notebook. We have many small unpartitioned CSV files, and although in this example we're only dealing with a few hundred records, in reality we're expecting many gigabytes per day in our production environment. We're going to quickly query that data to see what it looks like. When querying the data, we can see that we have an event ID, we have an event timestamp, and if I just scroll to the end, we have a user custom ID and a user domain ID. The user custom ID is just an email address and has a one-to-one relationship with the user domain ID. Although we can query this data as I have just done, as the dataset grows, query times will grow, and we can also see the header in the results. Ultimately, this is not fit for downstream processing, thus we want to process this in some way such that it can be queried efficiently and easily by our users. We've already installed ΑLaSpark from Git, so we're ready to go. In order to create a job, we must first have some config. ΑLaSpark uses Dynaconf to read its config files, which has some nice features such as allowing Ginger templating, as you can see here. Usually we would use a standard template that looks something like this, meaning that you only have to plug in a few values in order to get your pipeline up and running. This works well for some of our very generic pipelines that can be targeted at a number of different sources, such as just simple CSV or JSON pipelines. For the purpose of this demo, we'll be using this bespoke config. As our config uses Ginger, it can reference the environment as well as itself. You can see the deploy-env property references the environment variable of the same name that we've assigned above. This is assigned artichokes, as we're in the artichokes environment. At Gousto, we name everything after vegetables, so you might see a lot of this. We also have a schema name and a pipeline name. The schema name is of course the name of the schema that will be used to determine where we write the data, whereas the pipeline name is used to determine where checkpoints and bad records are written. This allows us to group pipelines together depending on the stage they are. For example, raw to processed. We have just called it demo pipeline here. We then have some locations to ingest from and to, as well as our bad records and checkpoints that are used for streams. We won't actually be using these today, as this example is going to be a simple batch job, but this is all the additional config required to turn this into a stream. And lastly, we have our source and target metastore database names. If we wanted to, all of this can be overridden with environment variables, which can be especially useful when changing log levels in production to debug some issue. We're going to write this config to the local file system. ΑLaSpark will pick this up when the job is started. With that out of the way, let's begin building our pipeline. First, we need a class to represent our job. It will inherit from the base job class in ΑLaSpark. This requires us to implement an execute method that simply takes some quarks, as well as providing a few other useful properties that we can use in our pipeline. I'm just going to call it Fake Web Events Job. The base job gives us some useful functionality such as the metastore database properties for the source and target. Let's verify this is set up correctly by printing out the name of the source database from this base property. In order to run this, we need an instance that we can call execute on. That's worked. This is the source database we created earlier. From this source database, we can build our pipeline. The source database object has a getTables method, which will return an iterable with all the tables we wish to ingest. In our case, a single table. Let's iterate over these with a for loop. Firstly, we need to set the pipeline name from the config. We do this by calling setPipelineName on the table object. This will return an instance of itself. Secondly, we will read some data using one of the readers. This table object has a read method which allows us to do this. We're going to use the CSV batch reader class to do this. In order to read CSV, we need to set some CSV options that we've already defined. The CSV options just set a few useful values such as the header, which is true, and the date and timestamp format. Let's assign this to a variable readTable. Using readTable, we can now get the underlying data frame. Let's display it using Databricks display function. As we can see, the job has read the data correctly. We're no longer seeing the header in the data, and we can see all the columns that were present in the raw data that we saw earlier. In order to do something useful, we must use a processor. This will transform the data in some way. Firstly, we will add some metadata such as the source file name and timestamp. This will tell us where the process data came from and at what time it was ingested. This can be helpful when debugging issues in the data. To do this, we simply call the applyToTableProcessor function and give it the processor class we wish to use, as well as any additional arguments. We've already imported some of the standard processors with the variable p. Let's display this data frame again and check that those columns have been added. We can now see the source file name and the demo pipeline ETL timestamp. Now, before we write the data, we probably want to add some partitioning. A good thing to partition on for our use case is date, but we don't have a date column currently. We can simply add this using the with column processor, which just takes a name and column expression. The column expression is just a PySpark column, meaning we can use the toDate function from PySpark. Let's check that's working correctly. And we can now see the date column 2022-03-12, which should match the date of the timestamp, which is 2022-03-12. We can now add our partitioning using the add partition processor. This just takes a partition column, which in our case is date. I'm not going to run this, as it's just adding some metadata to the underlying process table to instruct Spark to partition on the data on write. Therefore, we'd see no difference. We can now write our data using a writer. This could be done by calling the write method and giving it a writer of our choice. As we're using batch, we must use a batch writer. In our case, we want to write Delta, so we're going to use the Delta batch writer. Delta is a great choice here for downstream users. It offers great performance of Parquet with the addition of a transaction log, allowing transactional writes on the data, as well as time travel. The write method takes a few parameters. We need to give it the target database we mentioned earlier. We use the toGlueDatabase parameter for this with the target database property. This will either create the database if it doesn't exist in the metastore yet, otherwise just update it with the new schema. we're going to use the save mode, which we're going to set to overwrite. In reality, we'd probably use append for this use case with a stream, but for the sake of the demo, we're just going to use overwrite. Once this is finished, we should be able to query the data from our processor. One thing to note about this query is I've prefixed it with the word delta. This is because ΑLaSpark writes two tables by default, one referencing the delta table and the other referencing the symlink format manifest, allowing for the data to be queried from the likes of Redshift or Athena. We should now be able to see all our additional columns that are present in the process data. As you can see, all our additional columns are here: source file name, demo pipeline ETL timestamp, and date that we've partitioned by. Let's suppose that we're only interested in the most recent interaction a user had with our website, and we have a requirement to only store the most recent interaction. We therefore need to remove duplicate user domain IDs from our batch. Let's see what duplicates we currently have. As you can see, we have many duplicates here, which is of course a problem. How can we solve this? Fortunately, ΑLaSpark has a drop duplicates process that we can use. Let's add this to our pipeline. This just uses a window function, so we must provide it with a window partition column and a window order by column. In our scenario, we want to partition by user domain ID and order by the event timestamp. As we've set overwrite, we should only see the new data that we're ingesting. And now you can see that we only have a single instance per user domain ID.
Now we're going to take a look at what's happening behind the scenes in ΑLaSpark. ΑLaSpark provides us with a number of different readers and writers that support a variety of different file formats, such as JSON, CSV, Parquet, Delta, and Avro. We can also read from queues, such as AWS SQS. They also support reading and writing as either batch or stream, making use of Spark streaming. At Gousto, we are stream first, meaning that unless there's some specific technical reason to use batch, we default to streaming. When working with Databricks Autoloader, this provides a few benefits, such as checkpointing, which adds resilience to our data pipelines and eliminates the need to do things in batch. Creating a reader can be as simple as this. You just need to implement a run method. The base class simply takes a source table, pipeline name, Spark session, and a config object. It assigns the tables to the table property so we can access the source location we are reading from. The source table can also make the table schema available for us, which can be useful for formats such as CSV and JSON. Keyword arguments are then passed as options to the read options method, which simply adds a bad records path. We then pass the resulting data frame to the getProcessTable method, which creates a process table object that is then returned, allowing for subsequent processors and writers to be applied. Creating a new writer is equally as simple. The majority of the magic happens in the streaming query method. The rest is trivial and just involves creating a written table object from the streaming query, which handles our metastore interactions. Note the drop and create table method. This will ensure that our metastore is completely refreshed every time we reinitialize the stream. In the future, we'll be looking to move this into the micro batches themselves, allowing for seamless metastore updates from within the stream. Finally, the written table is then returned, allowing the developer access to its metadata from within the pipeline. And here's the magic from within the streaming writers. In reality, this is just a simple Spark streaming query. Here we apply our partitioning that the add partition processor sets on the process table. We set the format as well as adding options we pass to the writer. This will initialize the stream and begin reading and writing data. One of the core components of ΑLaSpark is the metastore module. This is what really simplifies writing pipelines because your metastore interactions are all taken care of for you. At Gousto, we use AWS Glue for our metastore, but this is designed to work with any Hive-compatible metastore. We've abstracted metastore databases and tables into simple objects that act as the start and end nodes of our pipelines. This also means that schema definitions can be handled outside of the pipeline. It is the responsibility of a data producer writing raw data into the lake to ensure their metastore database has the correct schema, either by keeping it updated themselves or using some sort of a data crawler. We've also expanded the metastore to work with non-metastore sources. This could mean a dataset on the lake somewhere that provides its schema and data definition in some file, for example. Using ΑLaSpark, you just need to provide a simple table definition that can read the file and give you the table schema, partitions, and location. In order to perform transformations on the data, ΑLaSpark provides us with some processors. Our processors are split into two types, to table processor and to many tables processor. The former takes a single process table object and returns a new instance of the process table. The latter takes a single process table object and returns a list of process tables. This is primarily used to explode single tables with nested data into several flat tables, adding a hash key for downstream users to join them back again. Some processes are trivial, such as adding a column, adding metadata, changing the partitioning, or filtering the data. Others are more complex, such as performing a union or a join. We also provide some streaming specific processes, such as deduplicating microbatches on a set of keys. This is especially useful for processing CDC data with multiple updates on the same record within the same microbatch. We've currently got over 35 processes, all of which we keep as generic as possible and fully compatible with the PySpark column type where possible. This helps keep them as expressive as possible whilst also ensuring ease of use. This table shows a few notable processes. As well as highly generic table and column-oriented processes, we also cater for specific use cases regarding PII and array types. PII processes allow us to either fully or partially obfuscate columns when processing sensitive data. The original data that was unobfuscated is then written to a separate table that can be accessed by downstream users with an access request. This allows us to stay fully compliant whilst not obstructing our users' needs for non-PII data. Our array utilities allow us to flatten nested data and arrays of data into relational tables. This makes heavily nested data more SQL-friendly to users who aren't as familiar with Python tooling, for example, PySpark or Pandas, or processing nested data in just raw SQL. Here we have the implementation of the select columns processor. This simply selects a list of columns from the data frame, updates the partitions in case one of them were not in the selected columns, and assigns these back to the process table before returning it. Another one of the key components in ΑLaSpark is the process table class. You can think of this as like a data frame in Pandas or the ND array in NumPy. It represents a table that has been loaded or partially processed that can be either written or have additional processes applied to it. It contains all the metadata of the table needed by the subsequent processors and writer to write the table to some target. It also tracks the processes that have been applied to the table, allowing writers to write this as metadata when the table is written to the target, giving us some additional data lineage. This snippet shows the process table class. You can see the apply methods that are used when writing ＡLaSpark pipelines. They simply take a processor class as an argument, followed by some keyword arguments that are then passed to the run method of the processor. The same approach has been used with the write methods, with an additional named argument, database. This is the target metastore database that we are writing to. This structure allows us to chain multiple processes together to create our pipelines. What's next for ＡLaSpark? Firstly, we are planning to open source ＡLaSpark sometime later this year. We hope that with some contribution from the community, we can really extend the use of ＡLaSpark. In terms of features, we're planning to provide integration with schema registries. This will remove our dependency on metastores for our schemas and provide us with much more flexibility in where we build our pipelines and the types of data that we can process. And lastly, we want to improve data lineage in ＡLaSpark, especially with Delta. This is very important for Gousto, especially when it comes to our B Corp status. It's imperative that we can drive trust in our data, especially when it comes to calculating things such as our carbon footprints, and good lineage will help us trace every aggregate back to the source. And that's a wrap. Thank you for listening to our talk on ÀLaSpark. We hope that you have a great time at the conference. We will be around virtually if anyone has any questions. Please just post them in the chat area and we'll do our best to answer them. Thanks.